In this video, we're going to focus on the electrostatic potential energy, and we're going to calculate it for a system of 2-point charges, and then a system of 3-point charges, and then a general system of n-point charges. And we will end this by analyzing what the electrostatic potential energy for a conductor is. I'm going to follow the layout of the slides, but I'm going to use this kind of blackboard for more details. So before getting into the system of 2-point charges, I wanted to remind you where we began this unit. So we began by defining the electric potential. This is the change of electric potential as the change of electrostatic potential energy divided by the charge. Okay, so we can use this expression to go back to the electrostatic potential energy. So the change in electrostatic potential energy that suffers a point charge is given because there is a change of electric potential is given by the product of this electric charge Q times the change of electric potential. Okay, so we, if you remember, we can choose the origin of the electric potential in any point, because what is important is differences of electric potential. So we're going to choose this origin of potential electric potential as the same point of the origin of electrostatic potential energy. And if we do this, we can integrate this expression and show that the electrostatic potential energy of a charge Q at a point where there is a electric potential V is given by Q times V. Okay. Another idea is relating this change of electrostatic potential energy with the work we have to do against the field. Okay. To see this, we are going to use the same expression and put here, instead of the change of electrical field, we're going to put its relation with the electrical field. Okay, so this amount here is the change of electric potential. Okay, so this is equal to Q times E times the differential of path. And if you remember, this is exactly the work of the electrical force. This is minus F times dl. So if you focus on this minus, you can see that this is exactly the work the work done against the electrostatic force. Okay, so the change of electrostatic potential energy is going to be equal to the amount of work we're going to have to do against the field to get the system as it is. And this is the idea we're going to use for deriving the electrostatic potential energy of a system of point charges. So we're going to begin by 2-point charges, okay? So imagine we have 1-point charge here, Q1, and 1-point charge here, Q2, and they both at a distance of R12. Okay, so we want to know what is the electrostatic potential energy of the system, and this is going to be the work that I have to do to against the field to get this to set the system of point charges. So we begin by having the 2-point charges at an infinite distance, and we begin bringing point charge 1 to its position. So this is going to be the work we have to do to bring point charge 1 to this position, and then we have to bring point charge 2 to its position. So we're going to call that W2, which is the work we have to do against the field to bring the second point charge to its position. So let's focus on the first charge. We bring the first charge, and this work against the field is going to be equal to Q times the change of potential, of electric potential, okay? So we begin by bringing Q1, and the final potential is V at 1, and the initial potential is V at infinity, because remember that they were both, before we brought them, they were both at infinity distance. So this potential is 0, because at infinity we're using the Coulomb's potential. And this potential here at point 1 is also 0, because by the time we brought Q1, there was nothing at Q2. So the whole potential in the whole region was 0. Okay, so it really, we didn't need to do any work against the field to bring the first charge. However, for the second charge, now there's already a charge. So this is going to be Q2 times the potential at point 2 minus the potential at infinity. This potential at infinity is 0, but the potential at point 2 is not 0 anymore, because we already had charge 1 placed there. So what is potential 2 when we already have charge 1? This is given by K Q1 R1 2. Okay, so this is going to be K Q1 Q2 R1 2. So the electrostatic potential energy of a system of 2-point charges is going to be given by K Q1 times Q2 R1 2. Okay. So now we're going to complicate things a bit further, and we're going to bring a 3rd-point charge. Okay, so we bring the first point charge, Q1. Okay, we bring Q1, so the electric potential energy of this system of 3-point charges is going to be the work we need to bring the first charge, plus the work we need to bring the second charge, plus the work we need to bring the third charge. So as in the first example, the work we need to bring the first charge is going to be 0, because there's nothing else there. So the potential at this point, when there's no other charge around, is just 0. So we don't need any work. For bringing point charge 2 to its final destination, this is going to be like in the previous example. It's going to be Q2 times V2, but when there's only charge 1. Okay, so this is going to be K Q1 Q2 divided by R1 2. Here I'm already taking into account that V at infinity is 0. Okay. Now, what about bringing the third charge? The 3rd-point charge, we put it there. And we're going to call R13 to the distance between point charge 1 and point charge 3, and R23 the distance between point charge 2 and point charge 3. Okay, so the work we need to do against the field to bring point charge 3 is the product of point charge 3 times the potential, the electric potential at point 3 because of the other 2 charges, minus the potential at infinity, okay, which is 0. Okay, so now we have to calculate what is the potential at point 3 due to the other 2-point charges. And if you remember, here we just need to use the principle of superposition. This is going to be the electric potential at point 3 because of point charge 1 plus the electric potential at 3 because of point charge 2. This is KQ1 R13 plus KQ2 R23. Okay, so the potential, the work we need to do against the field to bring point charge 3 when there is already point charge 1 and point charge 2 is equal to KQ1 Q3 divided by R13 plus KQ2 Q3 divided by R23. So if we put these 3 together, we will end up having the total electrostatic potential energy of this system of 3-point charges, which is going to be K Q1 Q2 R12, which is this work we needed to do against the field to bring point charge 2 when there was only point charge 1, because the first one To bring the first one, we didn't need to do any work at all. Plus this work we have to do to bring point charge 3 when we already have point charge 1 and point charge 2. So this is K, Q, 1, Q3 divided by R13 times plus K, Q2, Q3 divided by R23. So this is the total electrostatic potential energy of this system of charges. I leave to you to demonstrate that this is you're going to end up having the same expression if you bring the charges in a different order. This is, for instance, if you bring first Q3 and then Q2 and then Q1, you're going to end up having the same expression. Okay, so this is okay when we have not many point charges to bring, but if we have a big amount of point charges, this can be quite complicated, bringing all those point charges and calculated. So we're going to look for an expression that is valid for a set of n point charges, okay? And to do so, I'm going to define V1 as the electric field that we have at point 1 for all the other point charges. In this case, this is for point charge 2 and point charge 3, which is K, Q2, R12 plus K, Q3, R13. The same for V2 is going to be the potential at point 2 because of all the other point charges. In this system of 3 point charges, this is due to 1 and 3. This is equal to K, Q1, R12 plus K, Q3, R23. And the same for point charge, for the electric potential at point 3. It's going to be the electric potential at point 3 because of all the other charges, which are 1 and 2. So this is equal to K, Q1, R13 plus K, Q2, R23. Okay? So we go back to this expression, which is valid, and we're just going to expand it a bit. So this is going to be, U is going to be equal to this first term, but instead of putting it just once, we're going to put it twice, but divided by 2. So this is equal to 1/2 of K, Q1, Q2, R12 plus 1/2 K, Q1, Q2, R12. So this is this part here. And then I'm going to do the same with this. So this is 1/2 of K, Q1, Q3 divided by R13 plus 1/2 K, Q1, Q3 divided by R13 plus this last term, the same, 1/2 of K, Q2, Q3 divided by R23 plus 1/2 of K, Q2, Q3 divided by R23. Okay? So now, using this whole expression and these definitions, we can put U as 1/2 of, we take this one that depends on Q1, this one that depends on Q1, and we say that this is 1/2 of Q1 plus V1. If you see, this is KQ2 R12, which is here, and KQ3 R13, which is here. Okay, so this is that, plus this that I squared here, plus this that I squared here. I can take, this is 1/2 of Q2 times V2. Okay, and these two terms here are 1/2 of Q3 times V3. Okay, so now we've ended up with an expression which is much more easy to put in a contract form. So the electrostatic potential energy of a system of 3-point charges is going to be the addition from 1 to 3 of 1/2 Qi times Vi, where this Vi is the electric potential provided at the point where the point charge I is located because of all the other point charges. And this we can expand this expression now for a system of n point charges very easily by saying that the electrostatic potential energy for that system is going to be just the addition from 1 to n of 1 over 2 qi vi, where this v is the electric potential at point I provided by all the rest of point charges. Okay, so this is for a system of point charges. Now, before going into a conductor, I wanted to discuss with you what the electrostatic potential energy for a continuous charge distribution could be. So for a continuous charge distribution, now you imagine this continuous charge distribution here, and we're going to do very, very similar to what we've been doing. Remember that for point charges, we've been bringing each point charge from infinity in a way that we've been changing the electric potential. So the idea would be that the change in electrostatic potential energy due to bringing a point charge from infinity to this system. So this is dq. I bring it from infinity. Okay, so this is 0, its potential at infinity, and when I place it at this point is going to be v. So the amount of the increase of electrostatic potential energy, because I bring this charge dq from infinity to this continuous charge distribution, which had already electric potential v, is going to be given by this expression. So if I want to know the total electrostatic potential energy, what I have to do is to integrate. U is going to be the integral from 0 to big Q, where big Q is the total amount of charge of B ddq, where V is going to be changing as I'm adding more charge. Okay, and it's just the same idea. It's the work I'm doing against the field to set the final distribution. So this same idea can be used for a conductor. So a conductor is a body, a continuous charge distribution, okay, but that has a special characteristic because it has free charges to move around it. So if you remember, we came to the conclusion in this last video that the potential for a conductor is going to be proportional to the amount of charges it has, okay? And this proportionality depends on the geometry, okay? So for a conductor, imagine this is a conductor. I'm going to calculate the total electrostatic potential energy by adding small pieces. So at the beginning, I don't have any charge, and I bring some dq charge from infinity to the conductor. And then this is going to change the potential of this conductor. And then I'm going to bring another dq and place it in the conductor. And I'm going to charge it. So U is going to be the integral from 0 to the whole charge Q of the electric field times dq. Okay? So the idea now is that V, big V, that is the final electric potential, is going to be equal to some quantity that depends on the geometry times the total charge. However, at any moment, V, which is not big V, but just the potential at that time, is going to be also equal to this same constant that depends on the geometry times the charge that has at that moment. Okay? So when I want to do this integral from 0 to big Q of V ddq, I just have to remember this. This is the integral from 0 to big Q of alpha Q dq, okay? And this integral is a very easy one. This is just alpha square q divided by 2, and I have to integrate between 0 and big Q. This is alpha square big Q divided by 2, okay? And here I'm going to remember that alpha times Q is the final potential that the conductor is going to acquire. So the electrostatic energy of a conductor that has a charge big Q and a potential big V is going to be 1 over 2 times Q times V, okay? Which is quite similar in a way to what we got with the system of point charges. And expanding that, for a system of conductors, the total electrostatic energy is going to be the addition from I equal 1 to n of 1 over 2, the charge of the conductor I times the electric potential of conductor I, okay? This we're going to use quite also mainly in the capacitors. So with this, I end this session, but just before ending it, I wanted to tell you that now you would be able to do exercises 1, 5, and 6 that added to the previous video. Then you would be able to do exercises from 1 to 7, all of them, okay? So bye, and I hope this video was also useful for you.